Okay, so we've got this problem here. It's a machine problem because we've got a pair of pliers, and if you can see, we've got two little, I guess, handles of the pliers. Yeah, two handles of the pliers here. And they've got a little pin right here where they can kind of pivot around. There's a pin support there. And then they're both clenching onto this smooth pipe B right here. So if we read the question, it says, a force of 80 newtons is applied to the handle of the pliers as shown. Determine the clamping force exerted on the smooth pipe, which is B, and the magnitude of the force of the pin at A. Answers must be supported with relevant free body diagrams and equilibrium equations. Okay, so do you guys know where to turn to first? The very first thing you ever do in a problem like this? Free body diagrams, yes. So that's what we're going to do. They're going to be really ugly, and with the machine problems, they don't really expect you to make them beautiful, I suppose. So just try your best on these. I know I am. So I'm drawing this one first. And it's really bad. I'm going to draw this pin here at A. Okay. And so we are given, looks like the distance, well, we've got the force 80 newtons acting down here. And then, let's see, if you look here on this flat part here, this is supposed to be kind of the flat part. I didn't quite draw it right. But the flat part here, we've got the smooth pipe. Well, because we've got these both clenching on the smooth pipe, they're putting a force onto the smooth pipe, which means that the smooth pipe is therefore putting a force onto them. Does that make sense? So we've got this smooth pipe basically fighting back, which means that we've got a force here. And they ask for NB, so that's what I'm going to write it there. NB, and then we'll want dimensions. So we've got, I'm going to write it in meters, 0.250 meters. And then between A and NB, they're supposed to be perpendicular here, 0.050 meters. And then, let's see, we've got, always want to write in our AY and our AX because this is a pin. And that's basically what we've got, except we've got one more thing here. If you look right here that says 45 degrees, it basically means that this normal force here is acting 45 degrees to the vertical. So I'm going to draw a little line here. It might be a little confusing, like that. And I'm going to draw a little out here and say 45 degrees. Now, in an exam, you might want to draw it a little different way. Maybe draw the 45 degrees down here like it's drawn here. But just for the time being, so you guys can see what I'm getting at, that's going at a 45-degree angle. So we've got the free body diagram of the first one. I'm going to draw the second one, and I'll try to go a little quicker this time. So hopefully you guys understand it so far. So again, we've got the normal force acting on this flat part like we've got here, and B, and again that's 45 degrees. We've got AY and AX. Now we're going to want to draw them because these are two members with the same pin. If A is acting upward on this one, it's got to be acting downward on this one, because equal and opposite, whichever law of Newton that is, I can't ever remember. And then same with the X. If it's acting to the right, it's going to act to the left. And then we've got 80 newtons acting upward. So if we do that, 0.250 meters. And then another 0.050 meters. Do the free body diagrams make sense? Any questions about those? Okay, we'll go ahead and move on. By the way, if it sounds like I'm yelling, I'm trying to talk loud to make sure this can hear me, so I'm sorry if y'all are scared or something. Let's see. So if we're looking at this, we want to find this force here. We want to find AY and AX. Well, we've got three unknowns, and technically we have 6 equations we can solve for it, but we really only need 3 equations to solve for them. And so we'll take a look at this free body diagram. And I think the best thing that we can do now is we can take the moment about a point. Because if we were to try to sum forces in the y or the x, you're just going to get a mess with 2 unknowns in each equation, and they're going to be different unknowns. So you can't really simplify them. So instead what we're going to do is we're going to take the moment about A. So the sum of the moment about A is going to be equal to, and we're going to go through and look at all of our forces. So we've got this 80 Newton force, and it's acting 0.250 meters away from A there. And if we use the right-hand rule, we see that it's curving this way because it would be pushing it down, kind of looping it around that way. So that'd be positive, or counterclockwise. And then we'll be looking at NB over here, which the way I have it drawn is pushing on it this way, which right-hand rule, it's going in a clockwise direction, so that's going to be negative. And we're going to have NB times 0.050 meters, and that's going to be equal to 0, as always. And so what we're going to do is just algebra from here. You guys know the drill. It's going to end up being NB is equal to 400 newtons. And it just asks for the clamping force. It can't really be done in vector form because we just want the normal force here. So I'm going to go ahead and write it up in our answer box as well. 400 newtons. Does anybody, yeah?
So why do we not have to take the x component for the 800 or the NB because they're not on the same plane? Like, there's a height difference. Is it because we're just not given?
Oh, it's because, let's see here. So we've got the distance between the point and the force is always perpendicular,
Yeah.
right? If we look here at the point 50, if we look here at the point 50 millimeters, it's already given at the 45-degree angle. It's already perpendicular to where NB is acting. Does that make sense? So that's why, otherwise you would be right. We would take the x and y of NB in like another situation, but if the distance were given like that. But since the distance is already given perpendicular to where this line of force is, we can easily just take the 50 millimeters. Any other questions so far? Am I going through too fast? I feel like I might be a little bit rushing. No? Okay, good. I might as well speed it up then. No. We'll take the sum of the forces in the y next. From here on out, it doesn't matter. It's just your typical equilibrium equations, but I'm going to take the sum of the forces in the y. And so we've got the negative 80. We've got our AY going up. And then we've got our NB. And because we got 400 newtons, this means that this arrow was drawn correctly. So that means that in the y component, NB is pointing downward. So we'll take a negative. And NB we got is 400. So I'll just write in 400. And then we're going to want to get that into the y component, which this is 45 degrees. We'll take the cosine of 45 degrees to get it along the y-axis. You guys can see it up there, okay? Okay. So you got, this is our equation here. And when we end up solving for it, we'll add both of these to the other side. We get AY is equal to 362.8 newtons. I'm just going to do a little scribbly underline on that one because that's not quite our final answer yet. And then we're going to want to take the sum of the forces in the x. So if we sum the forces in the x, and we're still just looking at this one side here. In some other problems, you might have to look at both parts depending on how complex the machine is. But since the forces are mostly the same on both of them, there's no other forces, we can do what we're doing here. So our fx, if we look, we've got ax in the positive, and then we've got nb also in the positive. So it would be plus our 400 times, and this time it'll be the sine of 45 degrees. That's equal to 0. And AX is equal to negative 282.8 newtons. And so we've got our X and Y for the pin, but the question, and this is something you always have to be careful of on exams or any problem you work on, is it's asking for the magnitude of the force. So it's not asking in vector format. I know there were a couple problems on the tests or whatnot where it asked for vector component, and some folks actually went through and found the magnitude of it, and unfortunately they lost a point or two because of that. So always make sure you know what the question is asking and you put it in the correct form. And so we want FA. I'll just write this magnitude sign here. And so we write the magnitude sign. It's going to be, of course, the square root 362.8 squared plus 282.8 squared. And then when you calculate that out, it's going to end up being 460 newtons. And so we can go ahead and put that up in our answer box here. And that's how we solve. It's a fairly simple machine problem, but this was actually, pretty sure this was actually an exam problem at one point from a final exam a few years ago. So this might be the type of problem you could expect. Does anybody have any questions about it?
Just like, do you need to draw those free body diagrams for this one?
That's a good question. If we need to draw both free body diagrams or one, I would say it's always a good idea to draw both, just so you can see it. Because you might look at a problem like this and say, oh, they're going to be exactly the same, you only draw one of them, and you might find out you miss a force or whatnot. On something super simple like this, it doesn't quite matter, but it does say it must be supported with free body diagrams, plural. So I would say it's always the best bet. You can never do too much, you know. You can always do too little. And so if there's two components here, you might as well draw both free body diagrams. So good question. Any other questions? Okay, I'm going to go ahead and move on to another exam problem type thing. This is another machine problem. I'm going to go ahead and see if I can zoom in on this a little more. For you guys here, can you guys see that okay? Or is it a bit small? Yeah, it's probably a bit small. Okay. You good now? Okay, so here's this problem here. Hopefully you guys have read through what it's asking for. But essentially A, B, and C are all asking for free body diagrams. So we'll go ahead and start. The free body diagram of the handle, that would be this thing right here with the 30 pounds acting on it. I've got a little sketch here of the shape of the handle. And so this is, I just added, or had the sketch here of what it looks like. I've got the dimensions in there. And then this is acting, it's hard to see here, especially probably if you're looking at from up on the board. But this is a 15-degree angle down at the bottom. This should be level here, but it's not for now. And so we've got to find out what our forces are on this. The very first one we can see is we've got the 30 pounds acting on it that way. That's pretty simple to see. It's right there. And then I think the next easiest one is we look at O. It looks like it's pin connected here at O. And it should be able to move. If you were to push down, it would rotate around that there. So we'll go ahead and draw OY and OX. And then we also have a force at AB, which this is one case where you're going to want to look and see, is this a two-force member? Because if you do, it makes it a lot simpler and probably, in this case, makes it possible to solve. It might not be possible to solve if you didn't see that. So looking at AB, it's pin connected at both ends here. And if you look at it, there's no outside forces acting on it besides these pin connections. So therefore, it would be a two-force member. And so I'm going to go ahead and draw in there like so. Let's see. I drew it as a tension. I like to draw things as tensions for the most part to keep them, I guess, positive. That's the assumed positive direction. So we've got that. And then it's 15 degrees from the bottom here again. And so I'm just going to go ahead and draw it 15 degrees. I think it's like interior angle law or something like that. 15 degrees there. And we can write this. I wrote it as FAB. So any questions about that so far? No? Okay. I'm going to go ahead and move on to the free body diagram of shaft CB. And so looking at shaft CB, it is this one right here. This shaft just kind of sitting there minding its own business. If we looked at that, we'd have a force acting on it to the right. And it gives us, in the problem, it says the only support reaction is the smooth guide on shaft CB, and it's a normal force, which means that the only reaction we have on it is acting straight up. And I'll just label that as N. This one should be labeled as F. And then if we look at our picture one more time, we've got at B is connected to AB, so we've got force AB right there. And it's acting 15 degrees above because that's what force AB is acting at. Does that make sense to you guys too? Okay. And then AB, try not to mess this up. So you've got AB here, and I've got it drawn here. Because it's a two-force member, I'm just going to go ahead and draw the forces acting out like it's in tension, FAB and FAB. I'm going to go ahead and zoom out more on the screen here so we can kind of see the whole thing. Let's see. Okay, so we've got our A, B, and C done with the free body diagrams. Next, the question is asking for determine the magnitude of the force F. And so if we were to look through all of our free body diagrams and think, oh, how can we find F? The only one that includes F is our free body diagram of shaft CB. So I'm going to write up here, look at CB. And if we look at it, the only, force equation that we can use to find what F is going to be the sum of the forces in the X. So we'll take the sum of the forces in the X is equal to, we've got F acting to the right, and then FAB would also be acting to the right, and it's 15 degrees above, so we'll take that as the cosine 15 degrees, and that equals 0. Well, right now that's not very helpful because we don't know what FAB is yet. So what we're going to want to do is we're going to look at another free body diagram that includes FAB. If we were to look down at our free body diagram for C, it wouldn't really help us much because the only force on it is FAB, so there's nothing else to really help us solve for it. But we can look at our free body diagram here for A. And we can see that we have FAB here, as well as some others that we need to solve for. So what our game plan now, because we have three unknowns acting on this handle, we've got FAB, we've got OX, and we've got OY. The best option that we can do now just to solve for FAB by itself is to take the moment about O. So we can get rid of these two forces here in that equation and solve for the third. Does that make sense to everybody? Okay, if I'm going too fast, please yell at me or stop me or whatnot. So we'll take the moments about O. So I'm going to write down here, I'm going to give us some space to do some more work later on. Look at, and this is handle. So if we want to look at the handle there, we'll take the sum of the moments about O, and that's going to be equal. The first thing we've got is the 30 pounds. And then I'm just going to keep it in inches. Normally we would want to convert to feet because that's more of a standard unit. But I'm just going to keep it to inches because in a moment, and we're just solving for the force, it should even out to just pounds again. So we've got 8 inches there. And again, the dimensions are given perpendicular to this force here. And when that happens, we don't have to put it into any components or anything like that. So we've got that. And then we're going to want to find the moment caused by FAB. And that one's where it gets kind of tricky. And we don't exactly know what the angles are. So you're going to have to want to go back to your sketch here and try to get it into a component perpendicular to this line here. So I'm going to draw right here a set of axes like that. And we want the force along this axis down here. I'm not going to label them X and Y, but I'm just going to say we want the force going down in this because when it goes down here, it's going to be perpendicular to this line here, perpendicular to the distance away from O, and that'll be easy for us to solve. So we need to find what this angle is here. And so in order to do that, we know that this here is 15 degrees above, or it's going 15 degrees above horizontal. And when we know that, we also know that this is going to be 15 degrees right here. And the way I like to see that is if we had it like that, our axes turned like that, and we saw it, if we see that we turn this bottom one down 15 degrees, the top one would turn with it. Does that make sense? I'm visualizing that. So if this goes down 15 degrees, this has to go 15 degrees with it. It's just how they turn like that. And it's not exactly the most scientific or geometrically sound, I suppose, but that's how I visualize it. And so when we've got that, we also know this is horizontal here, and we can see that this is also going to be 15 degrees right here. So we've got 15 degrees down here. I'm going to redraw this just a little bit. So you've got 15 degrees acting from FAB to the horizontal, and then from the horizontal to this line of action here, we've got another 15 degrees. And again, one way you could visualize that is this is 15 degrees here, where the bottom of this is acting, and this line is still the same. So where it's 15 degrees to the horizontal here, it should be 15 here. Does that make sense to you guys? Okay. And so in total, this is all 30 degrees here. And so in order to get the force that we need, we're going to we want FAB acting down here, and when it acts down there using right-hand rule, it's going to be positive. So plus FAB. And then we've got the 30 degrees acting this way, so we're going to want to take the sine of 30 degrees to get it into this kind of vertical component. So we're going to take the sine of 30 degrees, and then the distance from O to where this is acting is 2 inches. And that should be everything that causes a moment about O. We'll set that equal to 0. And so you guys are going to do the math on this one. And once you do the math, you find that FAB is equal to negative 240 pounds. And that should make sense if we kind of look at our picture here. If we're pushing down on this handle, you should be able to see that this handle would therefore push down on AB, and AB would be in compression, which with our negative sign here, it means that these would be acting into AB, and that would therefore be in compression. So it lines up with what we can kind of guess. What's up?
I keep getting 121 for my force AB.
Did you get 121?
30 times 8 is 240.
30 times, oh, okay. 30 times 8 is 240. I might have messed that up in my calculations the other day. Yeah,
I got negative 121.
negative 121. Okay, I'll trust you. Thank you. Negative 121. So my apologies for that. So we take that, divide that by that, and we should get negative 121 according to that. That makes sense. And so using that, we're going to want to take this force AB and go back up to the equation we have up here and solve for F. So therefore, we're going to get F is equal to, and this is going to be negative 121, which makes it positive over here. So it'd be 121 times the cosine of 15 degrees. And therefore, what did you get for F then?
negative 91.9.
Negative 91.9. I'm going to say it's going to be positive. Okay. 91.9 pounds.
Oh, yeah, which is what.
Okay. And that'll be one of our answers. So 91.9. And so that's the magnitude of the force F. You can see down here, I wrote it out in the answer box down here, 91.9 pounds. And so that's our part, looks like part D. And so now we want to go on to part E. And so part E states, determine the magnitude of the pin force at O. And so from here on out, it gets more into force equations that we're probably used to seeing. And so when we take our force equations, we're going to want to look at the handle here because that's the only thing that has OX and OY. So our sum of the forces in the Y is going to be equal to, we've got the OY, and then we've got, I'm going to write minus 30 times, and this is again 15 degrees, how we visualize it up here. That's going to be minus 30 times, looks like the cosine of 15 degrees. And then minus, I'm just going to write FAB times the sine of 15 degrees. That's because it's 15 degrees to the horizontal here, so the sine would give us the vertical component. And that should equal 0. And then once you actually calculate it out, if you, what's up?
It is 240, by the way.
Oh, it is FAB is 240?
Oh, what's that? Why is that?
It's not 30 and 1/2.
Okay, so it is 240 then.
Sorry.
Okay, yeah, no worries, no worries. I trusted you. No.
Sorry.
No, you're fine. Don't worry about it. I'm just glad that. Okay. Felt really bad there that was wrong. So it is negative 240 like we have here. I'm going to go back. Thank you guys for clarifying that. 240. And so what I ended up getting for that one was 231.8 pounds. Do you guys agree with that? Okay. 231.8 pounds is what I got for F. So my apologies. We'll go back down here to OY. And so this FAB is going to be, like we have, negative 240. And so you want to substitute that in. And when you do that, you should get, or at least I got, negative 33.14 pounds for OY. And then you're going to want to sum the forces in the X kind of the same way. So sum of the forces in the X is going to be equal to, let's see here. We've got our OX, is what I'm going to write first. And we've got our 30, and this time it's going to be the sine of 15. So minus 30 times the sine, 15 degrees, right there. And then let's see here. We're going to again have our minus FAB, and this time it's going to be acting cosine 15. And those are the only other forces in the X. So we're going to set that equal to 0. In doing the math for that, we're going to get negative 224.1 pounds for OX. So those are our components for that. But again, this is where you have to be careful with what the problem is actually asking for. It's asking for the magnitude of the pin force at O. And so solving for magnitude, we're going to want O, I'll write it like that, is again going to be distance formula, 33.14 squared plus 224.1 squared. And I ended up getting 226.5 pounds. So does that make sense to everybody? I'm going to go ahead and write that down. And the answer key here. So that's how you would go about solving one of those problems. It's very intensive, I'm going to say. These machine problems aren't exactly my favorite. They're kind of fun once you know what you're doing, but they can be really confusing if you're not careful about them. So your lecture videos today should be a lot of reviews about machines and frames. So those would definitely be good for you guys to watch. So that's what I have for the machine problems here. And yeah, we can go ahead and start working on a third problem. I've got a frame problem for you guys to work on. So I'm going to run through one more problem here. And this one is also kind of ugly, like the last one we worked on. But it's kind of nice when it works out. Okay, so if we read the question, it says, the hoist pulley structure is rigidly attached to the wall at C. A load of sand hangs from the cable which passes around a 1 foot diameter frictionless pulley at D. The weight of the sand can be treated as a triangular distributed load, a maximum of 70 pound-feet. And then determine all the reactions acting on member ABC and show them on the report diagram in the form of magnitude and direction. So basically we're going to want to write our free body diagram for this, find out what all of the unknowns are, and then put it onto this here. And so I'm going to go ahead and start by drawing a free body diagram of ABC by itself. I'm not going to touch this yet until we get the forces, because they actually want the magnitudes on this. So we'll start with ABC. So if we look here, this is a pin connection here at A, which means we've got an X and a Y. And then BE, this is another one where you're going to want to look and see, are there any two force members in here? So BE or EB, either way, it is pin connected at both ends here, and there are no external forces acting on this part itself. So that's going to make it a two force member. And I'm going to draw it in tension like I tend to do. And I wrote it as FEB. So we've got those. And then the last thing we've got is the support reactions at C. And so for the support reactions at C, we've got CX, CY, and then we've got the moment going about C. So hopefully you guys all agree with that. This kind of gives us our basis for all the unknowns that we're trying to solve for. So we've got AY, AX, FEB, and the moment of C, and then the CX and CY. That gives us 6 unknowns in total. So that's kind of a lot we need to solve for. Of course, you're always going to want to put dimensions in here too. And so looking at our drawing, we've got 3 feet from the edge to EB. And then from EB all the way to A, we've got 2 feet and 2 feet makes 4 feet. So there's that. The next free body diagram I wanted to draw, just to make it a little easier for us, is the pulley, actually. You could go through and draw AE or ADE or whatnot, but I think it'd be easier to start with the pulley so you can kind of see what the forces are now. So we'll start with the pulley. I'll draw a circle. We've got tension going down here, and then tension going to the right here along that. And then on here, you're going to want to draw your support reactions, DX and DY, because it's a pin connection here where the pulley is. And I think with pulleys, you can kind of visualize and see what directions the force D should be going, because we're going to need opposite and equal, because we've got DY acting in the Y and in the X. To make sure this pulley doesn't move, it means that DX and DY are going to have to be exactly opposite of what these tension forces are. So DY is going to be acting upward against this tension force here, and then DX is going to be acting to the left against this tension force to the right. And so we want to solve for this tension force here. We've got this distributed load here. If we kind of line this out, knowing how distributed loads work, we've got the maximum of 70. We're going to want to multiply that by the length it goes over, which is 3. And because it's a triangle, it's going to have half the area. We're going to divide it by 2. And doing that, you get 105, looks like pounds. So this is equal to 105 and 105. And therefore, it means that dy is also equal to 105, and so is dx. And so those will come in handy when we draw our ADE. So any questions about that so far? Okay, good, we'll keep going. Let's see here, I'm going to draw a free body diagram here. So we drew AY going up, so we're going to draw it going down here. This free body diagram is from ADE. So AY is going down, and AX be going to the left. And then we are going to draw the opposite of DX and DY here. So we've got 105 and 105. And then we've also got FEB, which is acting in tension going down. So I'm just going to draw it going down here. FEB. So we've got that free body diagram there and all of our forces on that. We'll need dimensions. And so up top we're given 2 foot and 2 foot. So we'll do 2 foot, 2 foot, 1.5 foot, 1.5 foot. And so when we've got that, we're going to want to sum our moments about A. And I could go out and write this all out, but hopefully you guys know how to sum moments. I'm just going to go ahead and draw that. By doing this, we find out that force FEB is going to equal to negative 91.875. And then we'll do some of the forces in the X once we know that. We could do that without knowing FEB. But some of the forces in the X is going to make that, FEB is equal to. And so some of the forces in the X, we're going to want AX is going to be equal to a positive 105 pounds. And then some of the forces in the Y is going to lead us to AY is going to be negative 13.125 pounds. And that's when you add in FEB and the 105 here. So that's what we do here. If you guys want to see the math, you can email me later on, and I can send out a different solution set here. So now that we know these, we're going to want to look at our ABC. So ABC. And we're going to want to take, just looking at here, we know what AY and AX are, and we know what FEB is. So I started with the sum of the forces in the Y. And that gives us that CY is equal to 105 pounds. And that's going to be going upward. Then we could take the sum of the forces in the X, and that's going to give us CX is equal to 105 pounds, and that's going to be acting to the left. And then we're going to take the sum of the moments about C, which is going to give us that MC is going to end up being equal to 367.5 pound-feet. And so that's what we've got there. If we were to draw all of these onto here, what we want to do, we'll take a look at this free body diagram here. So we've got AY is going positive 105. That means it is going this direction. And so it's hard to see here in pencil, but AX is 105. AY is negative 13.125, so we'll draw it going down because I drew it going up here, 13.125. FEB is negative 91.875, so I'll draw 91.875 there. And then we've got CY is 105 going up, CX is 105 going to the left, and then the moment of C is 367.5 going that way. And you're going to want to include units on that. And those should be all of the unknowns that we have about that. So I'm sorry I kind of had to rush through that. We ran out of time a little quicker than I had anticipated, but that's the answer for that. I've got one quick note to make about this problem, though. To kind of check your work on this, we did this by taking each of these components individually. If you want to check your work for the CX and CY and the moment about C, you could also take this whole thing as a system by itself. Because if you look at it as a system by itself, you're going to get something like that. And then you're going to have your CY, CX, and then the moment. And so as a system by itself, you can take the sum of the forces in the x and in the y, and you'll end up getting the same thing. Because you see the tension is acting downward, 105, that means Cy has to act positively, 105 going up. Tension's going right, 105, Cx has to go left to counter for it. And then when you take the moment, including these and all the dimensions and whatnot, you're going to get that the moment C is going to be equal to the MC here, 367.5 pound-feet going clockwise. So I hope that made sense to you guys. I'm sorry I went kind of fast through that one, but if you have any questions about it, you can always email me. But did you guys like this today, or did you like how it was before? Would you rather me give you more time to work on the problems, or would you rather me just speed through them more or do more problems? So let's do show of hands. Who likes the old way better? Okay, and who likes today better? Oh, okay, yeah. Resounding yes. Okay, cool. Thanks, guys.